Now, let's introduce a little bit about the settling. And we have talked about Stokes settling, right? We have equation to calculate that, right? So, but in the real world separation, actually it's a little bit more complicated than Stokes settling, right? And here I'm illustrating Stokes settling. Basically, you have one particle settling in an infinite liquid. This is Stokes settling, and we calculate based on the Stokes equation, right? And here's the settling velocity as a function of solid concentration. Okay, and then once the concentration become higher and higher, then we start to get into a region called hindered settling. Why it's called hindered? That means the solid particles start to affect each other. Larger particle based on Stokes settling will settle faster, and small particle will settle slower. But because they are affecting each other, influence each other, so larger particle will drag the smaller particle down, right? So smaller particle will settle faster. So you will find that once the solid concentration become higher and higher, then you can see the solid, everything seems to be settling at the same speed, and then you can see a clear interface at the top. So we call it zone settling. So if you look at the right-hand side pictures, and here's the clear liquid on top, and you can see, although this is not very clear, but well, in a practical sense, this is kind of clear. You can see a clear interface between the clear liquid and water and the settling slurry, right? So it's here. Okay, so this is called hindered settling, and in this region, the solid concentration, the solid settling velocity is a function of concentration. That means at one concentration, you only have one settling rate because everybody is settling at the same rate. The bigger one drag down the small ones, the settling rate. So you can see the settling velocity as a function of concentration. You have one single curve over here, right? And in comparison, this is a Stokes settling. You can see no clear liquid, and you can see particles everywhere, right? But you can see, if you can pay close attention, looks like it is clearer at the top, a little bit more cloudy at the bottom. That's simply because solid settle at the bottom. A larger particle goes down faster, the smaller particle comes down slower. And this is the representation of the Stokes settling, and this is zone settling. And zone settling also called hindered settling, right? So you may hear this term if you dig into this. Now, when the solid concentration become even higher, and they are in physical contact with each other, actually maybe sitting on top of the other. In this settling zone region, we call it compression. Because over here, the settling velocity still depending on the concentration. So you can see all this dotted line is depending on the concentration. But in addition, one more factor will affect the settling, which is the height of the sediment. Because each one is sitting on top of each other, right? So the taller the sediment, the higher the weight of the solid. And the weight will compress and press the sediment to settle down. So the higher the sediment, the faster the settling rate. So you can see the settling behavior actually is a little bit complicated than just Stokes settling. Where you have zone settling, the settling rate is a function of concentration. And once you go to compressing zone, the settling rate is not only depending on the concentration, but also depending on the height of the sediment, right? So just bear in mind that when you look at the settling behavior, you need to have all this in mind.